Hello everybody, I'm Adam. In this problem, for the planes given by our two equations, 3x plus 2y minus z equals 7, and the plane given by x minus 4y plus 2z equals 0, we're going to be finding, for part A, the angle between the two planes, and then B, a set of parametric equations for the line of intersection of the two planes. So let's start with part A, finding the angle between the two planes. So to find the angle between two planes, we can start with what we know, that the cosine of the angle between the two planes, which we'll call theta, is equal to, say, the absolute value of the dot product between vectors n1 and n2 divided by the magnitude of the vectors n1 and n2, where n1 is a normal vector to one of the planes and n2 is a normal vector to the other plane. So to help our labeling, let's just go ahead and call our top equation, that'll be our first plane, and the bottom equation, that'll be our second plane. So in order to find, at least starting with the cosine of the angle between the two planes, we need to find our n1 and our n2. So n1 we can find pretty easily just looking at the equation of our first plane. So the normal vector is going to have components which are the coefficients in front of x, y, and z. So n1 is going to be equal to the vector with components 3, 2, and -1. And then n2 is going to be the vector with components with coefficients in front of, again, x, y, and z. So components 1, -4, and +2. All right, using these then, we'll find the cosine of our angle theta, and then after that, find theta itself. So we have cosine is equal to the absolute value of the dot product between n1 and n2. So with our dot product, we take component-wise multiplication and add everything together. So 3 times 1 gives us 3, plus 2 times -4, -8, plus -1 times 2, -2, and then divided by the magnitude of both n1 and n2. So the magnitude, we have the square root of the sum of squares of the components. So for n1, we have the square root of 3 squared plus 2 squared plus -1 squared times the square root of the magnitude, we're finding the magnitude for n2, the square root of 1 squared plus -4 squared plus 2 squared. Okay, and we'll go ahead and simplify everything. So looking at the top, 3 minus 8 minus 2 is going to be the absolute value of, say, -7. And on the bottom, we'll have the square root of 3 squared plus 2 squared plus 1 gives us 14 times the square root of 1 squared, or 1, plus -4 squared, 16, plus 4 gives us 21. Okay, so cleaning up the bottom just a little bit. So if we notice that 14 is 2 times 7, and 21 is 3 times 7. If we were to combine the square roots, we'd be combining all of these as a product. But we notice 7 times 7 under the square root would just be 7. So we can bring this out. On the bottom, we'll have 7 times the square root of 2 times 3, or 6. And on the top, absolute value of 7, -7, is 7. So our 7's will cancel, and we'll have 1 over the square root of 6. So that's our cosine of theta. We could leave it like that, but we can rationalize the denominator by multiplying top and bottom by the square root of 6. So this would give us the square root of 6 over 6. So there's the cosine of theta. What we want is the angle theta itself. So for theta, well, that's going to be equal to the cosine inverse of our value, root 6 over 6. And see, what's that going to give us? And we'll find this in degree mode. So cosine inverse of square root of 6 divided by 6 gives us approximately, say, 65.91 degrees. So that's our angle in degrees between our two planes. So now what we want to do is, for part B, we're going to find the set of parametric equations for the line of intersection of the two planes. So for B, and to help us get the idea, we'll take a look at a little picture. So we have two planes, call it plane 1, and our second plane, call it plane 2. And what we want to do is find the line of intersection between our two planes, right, made by these. So that's what we want to do, or the set of parametric equations of that. So to find the set of parametric equations of a line, what we need is two things. We need a point on the line, say some point P, and then we need a direction vector, or a vector that's parallel to that line, which we'll get to that in a moment. So first let's find a point on the line. And we can do that by simultaneously solving our set of linear equations of our two planes. So we have those, right, is 3x plus 2y minus z equals 7, and x minus 4y plus 2z equals 0. So simultaneously solving a system of equations, what do we do again? Well, what we're allowed to do is we can multiply through equations by a given constant, and then we can add the equations together by adding the corresponding coefficients. And what we want to do is to get one or more of the variables to drop out so we can solve for the remaining variables. So if we take a look at this and see, well, we have 3x plus 2y and minus z, and looking at the next one, we have x but minus 4y and plus 2z. So if we take a look, if we were to say multiply our top equation through by 2, that would give us 6x plus 4y minus 2z equals 14. Now, if we add these two things together, we see that the y's, the plus 4y and negative 4y will cancel, and the minus 2z and positive 2z would cancel, leaving us with just x. So 6x plus x gives us 7x. The y's and z's cancel, and then 14 plus 0 is just 14. So we have 7x equal to 14. Well, that implies, dividing through by 7, that x is going to be equal to 2. So we have the x-coordinate of at least the point on our line is x equal to 2. Now to find y and z, we can take the value 2 and plug it back into one of the two equations. Doesn't really matter which one. We'll go ahead and plug it back into the original first equation, or the top one. So we'll have 3 times 2 plus 2y minus z equals to 7. Okay. Well, 3 times 2 gives us, say, 6. So solve for one of the variables. We'll go ahead and solve it for y. So we have 2y, and if we add z and subtract over 6, 2y will be equal to positive z plus 1, and then dividing through both sides by 2, we have that y is equal to z plus 1 divided by 2. Now, how can we use this? Well, we can pick a particular value of z, plug it in, and solve for y. So if we take, say, z equal to 1, right, this implies that y is equal to, right, 1 plus 1 over 2, or 2 divided by 2, we get 1. So our point, I'm going to write it over here, our point on the line, which we're calling P, is going to be P with x-coordinate 2, y-coordinate 1, and z-coordinate 1. Okay, so we have our point on the line. The next thing we need is a vector or a direction vector that's going parallel to that line. How can we find that? Well, if we notice, going back to the part A, we have these two normal vectors. So we have a vector in our plane 1 that is perpendicular to the first plane, and we have a vector in plane 2 which is perpendicular to plane 2. Okay? So what we can use the fact is if we take the cross product between any two vectors, the resulting vector is orthogonal to the original two. So we can take the cross product between n1 and n2, and that'll give us a vector that's orthogonal to those. We're going out this way, or namely which will be parallel to our two planes, or in particular parallel to the line of intersection. So the next step is we're going to take the cross product between n1 and n2. So n1 crossed n2, and once we get that vector and we have our point, we can find our parametric equations. So our cross product will use our determinant form. So take the determinant of our 3 by 3 matrix. Our top row is the unit vectors I, j, and k. And the next row is the components of n1, which we have as 3, 2, and -1. And last row, components of n2, which we have as 1, -4, and +2. Okay. So leave ourselves some space and find the numbers in front of I, j, and k. So again, with the determinant form, for a number in front of I, we're going to cover up the I column and take the determinant of the 2 by 2 matrix of the entries that are left. So multiplying through by our diagonals, so 2 times 2 is 4, minus -4 times 1, -1. So that's 4 minus 4, or just 0. For the number in front of j, we're going to cover up our j column and multiply with our diagonals 3 times 2, which is 6, minus 1 times -1, which gives us 7, and cover up our k column. 3 times -4 is -12, minus 2, so it gives us -14. So our vector, and we'll just write this in component form, because that's all we really care about, is going to be 0, -7, and -14. Okay, so now to put this into practice. So for our parametric equations, we're going to have parametric equation x equal to x1 plus a times t, y equal to y1 plus b times t, and then z equal to z1 plus c times t, where x1, y1, and z1 are the coordinates of the point on our line, and a, b, and c are the components of our direction vector. So looking at our direction vector, we're actually going to simplify this just a little bit, noting that two vectors are equivalent if they're parallel or scalar multiples of each other. We can rewrite this vector as, say, -7 times a vector with components 0, +1, and +2. So that's what we'll take as our a, b, and c. So finishing up our parametric equations, we're going to have x equal to x1, which is 2, plus a, which is 0 times t. So we'll just have x equals 2, and y equal to y1, which is 1, plus b, which is 1, times t. So just 1 plus t. And lastly, we'll have z equal to z1, which is 1, plus 2 times t. So there's our set of parametric equations of the line of intersection between our two planes. Thank you very much.